A phase diagram specifies the physical state of a substance as temperature and pressure varies. The diagram consists of regions separated by lines. Each region displays the conditions at which a particular phase is stable. Each line between two regions displays the conditions at which those two phases are in equilibrium. This phase diagram is typical for most substances. In general, lower temperatures and higher pressures correspond to the solid phase. Higher P and T correspond to the liquid phase, and lower P and higher T correspond to the gas phase. Let's take a closer look at the diagram and view the various parts on the molecular level. A magnified view within the solid region shows the regular array of tightly packed particles typical of a crystalline solid. Note that the particles in a solid are not fixed, but jiggle in place about their crystal sites. A magnified view of the liquid reveals a major difference between it and the solid. The particles are still in close contact, but their positions are much less restricted than in the solid, and they roll and tumble around one another. In stark contrast to the solid and liquid phases, a magnified view of the gas shows the particles far apart except when they collide. At any point along the solid-liquid line, the phases are in equilibrium. Melting and freezing are occurring at the same rate. In other words, the same number of particles are moving from the solid to the liquid per unit time as are moving from the liquid to the solid. Similarly, at any point along the liquid-gas line, vaporizing and condensing are occurring at the same rate, which means that the number of particles moving from the liquid to the gas per unit time equals the number moving from the gas to the liquid. Finally, along the solid-gas line, subliming and depositing are occurring at the same rate. That is, the same number of particles are moving from the solid to the gas per unit time as are moving from the gas to the solid. Two other features of the phase diagram are important. The first is that the liquid-gas line ends at a point called the critical point, beyond which the distinction between a liquid and a gas disappears. Let's close in on this point and 2 points very close by to see what this means. At a nearby point in the gas region, the gas is under very high pressure, so the particles are reasonably close to each other. Thus, the density of the gas is relatively high. At a nearby point in the liquid region, the liquid is at a very high temperature, so the particles are beginning to separate from each other. Thus, the density of the liquid is relatively low. As these 2 points approach the critical point, the particles in the gas move even closer together and the density increases, while the particles in the liquid separate even more and the density decreases. At the critical point, the densities become equal and the phase separation between liquid and gas disappears. The second important feature occurs at the junction of the 3 phase boundary lines. At this point, called the triple point, the 3 phases are in equilibrium simultaneously.